So in the previous session, using a work diagram, we concluded that for any reversible process, it's always possible to find an equivalent reversible zigzag path between the same two initial and final states, which consists of an adiabatic process followed by isothermal, again followed by adiabatic, in such a way that the heat transfer during the isothermal segment of the zigzag path will be same as that of the heat transfer during the original entire process. Now we will be using that conclusion to analyze a smooth closed curve denoting a cyclic reversible process. So let's consider a smooth closed curve on the generalized Vogt diagram or the indicator diagram for a reversible cycle. A closed curve denotes a cyclic process. So let's see in the Vogt diagram here shown in the slide, you can see a closed curve here, right? Some arbitrary shape, an elliptical closed curve. So you know that the Carnot cycle was a very typical and idealized curve, but a closed cyclic process can be represented by a curve of any shape, because the path can be in general pass through any of the places, okay? So any of the points in general. It's not an idealized one, but see that let's assume that this is a reversible cyclic process. So that is the the elliptical curve that has been shown over here, the curve here. So now what we are going to do is that let's make some constructions in the lines of our discussion that we have done in the previous video. See, let's imagine the entire cycle or the entire curve be divided into a large number of strips. See, what are these strips? You can see that we have just made some strips like see this AD, then you have got some BC, then FG. Like this, there are large number of strips. We are dividing like this curve into large number of strips this way. So this is what we are going to do. Okay, imagine that the curve is divided into a large number of strips, and see that these strips, let them be adiabatic. Let these strips be adiabatic curves in the diagram, and let these strips divide the cycle into a large number of parts. Now let's imagine also two isothermal processes. I'm considering the first strip over here. So I'm considering two isothermal processes. One is AB. So this is one AB. This is the AB, and let me say another isothermal process here. Let that be DC or CD. I can say CD. AB and CD be the two isothermal curves. That just connect the two adiabats here, so namely AD and BC. Now let's say that during the isothermal process AB, let an amount of heat Q1 be entering the system. An amount of heat Q1 enters the system during AB, and see, during this CD, let an amount of heat Q2 be leaving the system. So now you can just see that what actually we have done. See, you consider this particular part of the reversible cycle. What I am just drawing now, this part, right? So this part of the reversible cycle, if you name this point as I and this point as IF, can you see that this IF has now been divided into three or some sub segments, zigzag path. So what is the zigzag path? I, A, B, F. I, A, B, F. Okay. What is the criteria? That whatever area is lost here, whatever area is lost here will be gained here. Okay, it will be gained here during IA. So whatever area is lost from the cycle, IF, through B will be gained by the path IA. Okay. So this is what we have discussed. This particular part only we have discussed in the previous video, where we have concluded that any reversible path can be imagined equivalent to a series of zigzag paths consisting of two adiabats separated by an isotherm. So IA is an adiabat, BF or BF is another adiabat, and they are separated by what you call as what AB as the isotherm. Okay, so this is what is happening here. Same thing has been repeated here in the bottom side of the diagram also. So the same process you can repeat with any other segment. You can just take this particular segment. This next one is taken this segment. Okay, and then you repeat the process for this particular segment, repeat the process for this segment, repeat it here, repeat it here, repeat it here. Okay, and you repeat at every part of this particular thing. And if the strips are pretty close or infinitesimally close, you will see that this particular thing will be equal to, or the area under this zigzag patterns will be equal to the area of the actual curve, which was something elliptical in nature here, which is a smooth curve. The area will be equal. So there is mathematically the process will be equal, and that actually is something very close to the process of the concept of integration, where you know that integration is just like a continuous summation, right? Okay, so the same thing is done here. So what we have done here is that I'm taking a small strip out of this curve. So just look at the strip here. What is the strip here? I'm naming the strip as I'm naming the strip as A, B. Try to follow that in the slide. A, B, C, D. I'm naming the strip as A, B, C, D here, right? So the strip you can identify here. This is A, this is D, and coming through the dotted lines, this is C, and this is finally D. Okay, and I can go back to A, B, C, D, A. Let me go back. So that is a closed curve. So what about the two sides? Okay, what about the two sides of the curve? You know that by our construction, AB as well as CD, AB and CD are two isotherms. Right? AB is at temperature, assumed to be at temperature T1, and CD is an isotherm at another temperature T2, say, right? And what about the other two curves? The other two curves are BC and what? DA, BC and DA. What about these two? These two are adiabats. And always just verify that adiabats connecting to isotherms will be always what? Steeper than the other one. So this is adiabat. So these two are adiabats. So now what you can conclude about the curve ABCDA? Can you see that it's closely resembling some sort of a Carnot cycle? So I can say that ABCDA will be representing a Carnot cycle, which represents a reversible cycle. Okay, so every assumption is okay. So what's our conclusion? This strip, or each of the strip into which we have divided the actual reversible path, will be representing a small Carnot cycle, right? And if you consider the first Carnot cycle, okay, so which we have named as ABCDA, you can see Q1 heat enters at temperature T1 and Q2 heat leaves at temperature T2. So Q1 heat is entering at temperature T1 and Q2 heat is leaving the cycle at a temperature what? T2. Is right? You always recall our Carnot cycle diagram. So hope you remember that it was during the isothermal processes that heat enters the system and heat leaves the system. Right? Okay. So now can you write some conclusions that we have used for a Carnot cycle? What is the conclusion? Hope you remember that in the case of a Carnot cycle, we had for a Carnot cycle, in general, we have seen that the conclusion was that we had a ratio TL by TH. Hope you remember that. What is TL by TH? TL by TH was equal to the corresponding heat ratio, that is QL by QH. That was our conclusion. TL by TH was equal to QL by QH, that we concluded. That's why we wrote the efficiency equation either in terms of TL and TH or in terms of the corresponding QL and QH. So from this, can you just conclude that if you rearrange this one, you can write this one QL by, you take the corresponding TL to the denominator here, QL by TL will be equal to QH by TH. This is a result that we have obtained from the general theory of Carnot cycle. Right? So if you apply this particular conclusion to our present small Carnot cycle A, B, C, D, A. So therefore for A, B, C, D, A, the first Carnot strip in the diagram, what will be the equation? Instead of QL, I can say Q1, right? So I can write this one as what? Q1, okay, by corresponding temperature there is what? T1. Q1 happens at T1. Q1 heat entry happens at T1. Okay, that should be equal to Q2. Q2, I am writing modulus, okay, as usual. Q2 and Q2 heat transfer occurs at a temperature T2. This is the thing. So Q2 divided by T2. Q2 by T2. Is it okay? Now, let's apply some sign convention here. By usual sign convention, whatever heat entering the system will be taken as positive, and the heat going out of the system will be taken as what? Negative. So as such, you can see that this Q2 should be negative. If you apply the sign convention here, Q2 will be negative. So what will be the fate of this equation? So this one should be, now I am avoiding this magnitude, okay. So let me use the sign convention also. I will be writing Q1 divided by T1 equal to minus Q2 by T2, and I am bringing that minus Q2 to the other side to become plus Q2. So what will be that one become? It will become plus Q2 by T2, and that should be equal to 0. Hope you understood how I arrived at this equation. Okay, so this is just by applying sign convention. You note the difference from this equation and this equation. Here I have been using the modulus sign, and here I have get rid of the modulus sign and have added the sign convention. From negative, Q2 is negative because it is going out of the cycle as you refer to the diagram. So this is one equation that we have got. Q1 by T1 is equal to Q2 by T2 that we obtained from the first strip in the diagram. Similarly, you can go to the second Carnot cycle in the diagram. So what is the second? Which is the second Carnot cycle in the diagram? That is E, F, G, H. So you can just assume like this: E, F, G, H. Then coming back to okay, of course it's a cycle. So coming back to E. So let me go to the next page. So just have a look at this one. Yeah. So the diagram, I'll make it a bit bigger. Okay, fine. See in the diagram, so this is our focus now. E, F, then through this way, G, then it will come to this one, this is H, and then finally coming back to E. So you can see that the heat entry that is happening here is one is Q3, Q3 heat enters at a temperature T3 and Q4 heat leaves. You can see the arrow here during at a temperature T4. So that is the way in which it's done, right? So for Carnot cycle, these are all small Carnot cycles. Okay, E, F, G, H, E. I can make it thing. So what you can write in the same way we have written the previous equation, I can write Q3 divided by the corresponding temperature T3 plus, is it not? Q, because it was taken from the other. Q4 divided by the corresponding temperature T4, that will be equal to 0. So let me say that this is my second equation. Similarly, won't you be able to write many other equations, like you can take here as Q5, here as some Q7, Q9, okay, likewise, and on the bottom you can write Q6, okay, then Q8, Q10, likewise. So there will be corresponding different temperatures also, right? So in the same way, you can just add all these equations and so on, you can say, and so on, that's enough. You'll be getting equation 3, 4, 5, etc. so on. Okay. So now let us add all these equations corresponding to the different Carnot cycles. What you will be getting? You will be getting an equation like this. Adding. Okay. So what will be getting? I'll be getting Q1 divided by T1 plus Q2 divided by T2 plus Q3 divided by T3 plus Q4 divided by T4 plus etc. Okay, any number of terms, that will be equal to 0. That should be equal to. Or can you just write this one okay, in brief? So, or I can use some summation sign, summation over some j or I, okay, Qj divided by the corresponding temperature Tj, that should be equal to 0. Qj by Tj equal to 0. Okay. Now here we have taken Qj as some finite value of heat entering or leaving the cycle or system, and Tj is the corresponding temperature at which the heat entry or heat transfer occurs, right? Now, if the adiabats are infinitesimally close together, so means these all adiabats, which are adiabats here, AD, BC, FG, all these are adiabats. If these adiabats are infinitesimally close to each other, okay, means we are dividing the process into very small strips, each representing a Carnot cycle. Then this I can say that these isothermals are also infinitesimally close, okay, or all these are infinitesimal isothermal processes. Then what we can do is that we can replace the summation with a corresponding integration. We can replace the summation with the integration. Okay, so let me do that in the next thing. So if adiabats are infinitesimally close, if adiabats are infinitesimally close, okay, then summation can be replaced with the integration. That's all, right? And that's actual way. Now, what to be the previous equation? So I'm writing instead of summation, I'll be writing what? Integration, right? And the process is cyclic, so I should be putting a circle over this one. The circle denotes what? Cyclic. And what was there? It was Qj by Tj. Earlier it was Qj by Tj. But you know that if the process is infinitesimal process, this Q should be something like d bar Q, right? So Q will be replaced with what? D bar Q, because it's an infinitesimal amount of heat transferring. Okay, d bar because it is inexact differential. So in place of Qj, I'll be writing d bar Q divided by, of course, T. Okay, no, there is no need of, okay, because T I'll be making as T, because T is a constant, right? Because it's the isothermal part. It's a temperature at which this d bar Q heat is entering or leaving the system. So I need not say which T. I should not say dt. We never commit such a mistake. So T is a temperature at which d bar Q heat is what? Entering. Okay. So that is because it is representing an isothermal process. That's why we are writing T itself. Do not replace by dt. That's a serious error here. Okay, so d bar q by t, and that should be equal to 0. That should be equal to 0. One more thing, what kind of a process we are discussing? We are discussing this one for a reversible process. So in order to show that this is representing a reversible cycle, I should write here as R in order to distinguish it from a possible irreversible process. So I am writing it here as R. Now we have come to a very important result, and this result I think you can recall. You have already seen this one in the introductory video on the Clausius statement, mathematical statement second law. This is nothing but the reversible part. This is nothing but, this equation is what is known as the reversible part of the second law of thermodynamics. Second law, mathematical statement. Okay, second law. And I told you this is better known as Clausius theorem. Clausius theorem. See, word of caution for you. There are so many things which may look similar, but try to understand in relation to the topic that we are discussing. Clausius theorem is nothing but the reversible part of the mathematical statement of second law of thermodynamics. Okay, mathematical statement, right? So that is closed integral over the reversible path. D bar q of t will be equal to always 0, and you can see this is an equality. This is an equality, and the inequality of this one will be for applicable for irreversible process, which will be named as what? The Clausius inequality. That will be just discussing in the maybe in the next sessions. So that's about the reversible part of the second law, and so far we didn't use the term entropy. It's a suspense figure that is yet to creep into our lecture that we will do in the next video. Okay, thank you.